In this video, we are going to do a pretty brief introduction to what an exponential equation looks like. So an exponential equation in general looks like this, where it's a times b to the x. All right, so the a value represents an initial amount. Okay, and that could represent a lot of things. That could represent a population, that could represent a salary, that could represent an hourly rate, that could represent a whole lot of different things. But your A is always going to represent an initial amount, and your B is always going to represent your multiplier. All right, so technically, there's a little bit of a different look to this. Is this equation kind of breaks down more into this look, where it's 1 plus a rate raised to a power. That's what your B consists of. It always consists of 1 plus a rate. If your rate's negative, then it's going to be subtracting from the 1. If your rate's positive, then it's going to be adding to the 1. So if your rate is positive, your value is going to increase. Whatever you're starting at is going to go up over time. Typically, your X represents time. Not always, but typically. And if your R is negative, you're depreciating. You're losing value. You're losing a value over time. And so it's going to take your initial value, it's going to decrease it. Okay, so that's kind of a quick, brief overview of it. Let me give you an example, and then we're going to start talking about compounding interest. A little bit more of a taking this equation, but making it a little bit different. Okay, so here's your idea. Let's say you started some sort of a job and you were making $20 an hour. And you got so there's two options for your raise. Let's say you got $1 raise every single year. You got $1 raise and it's consistently $1 raise, that is a linear kind of a pattern. So that means you were looking at an mx plus b kind of a thing. All right. B would represent your initial amount on this equation. Okay, that b has nothing to do with that b. They're different ideas. So if you remember a linear equation, that's your slope, that's your y-intercept / initial value. So if you started a job that was going to start you at $20 an hour and give you $1 raise every year, you would have 1 as your slope. Your x would represent your number of years plus 20. Okay, so that's a linear pattern, constant add or subtract kind of a pattern over and over and over again. An exponential pattern is still going to be a pattern, but you'll start with this dollar or this $20 an hour, and then you're going to have 1 plus a rate. And let's say you're getting a 5% raise. Okay, so 0.05. And then that's still going to be raised to a power. That x is the same as this x. It's going to represent your years. So let's say they're going to give you a 5% raise every single year. So which ends up being a little bit better. So this would simplify to 1.05. Okay, so since this is bigger than 1, it's going to increase because you're going to be multiplying by 1.05 over and over and over again. Just depends on what your power is. So here's the difference. So if you start off with a linear pattern, you're going to start with $20 an hour. And then your first year, after your first year, you're now going to make $21 an hour. And then you're going to add 1 again. You're going to make $22 an hour and over and over and over again. With an exponential, you're going to start with $20 an hour. And let me kind of break this up. You're getting a 5% raise. Well, that equates to $1. So it's the same kind of a raise. So now you're sitting at $21 the next year because I took the 1 and added it to what we were already making per hour. All right, but the next year, you're getting a 5% raise. You get a little bit more because your raise also got a raise. So that's the biggest difference is now you're making $22.05, right? So, and then now you get another raise. So now it's $1.10 that year. This was $1.05 raise. This is $1.10 because you're gained a 5%. It's your raise that earned a raise that also earned a raise, kind of a thing. So that's the power of exponential. So let me show you the bigger power of it. If you put this into the calculator and I graph or I type in that equation, so I have my $1 raise per year starting at $20, and then I compare that to a $20 with a 5% raise each year, what's the difference? So I'm not going to do a graph. I'm going to do a table. So if I go second table, all right. So here's where we're at first, very first starting year. And then after 1 year of work, we're at the same salary. We'll get a dollar raise. But this is the exponential. So this thing is getting that percent raise versus this getting a constant dollar raise. So your percent is the raise getting a raise year after year after year. So it's compounding is what we call that. So all of a sudden, if you're 10 years into this job, you'd be making $30 an hour here versus $32.57. Now, if you in terms of a salary, the idea is that you work about 2,000 hours a year. So if you take 30 and multiply it by 2,000, that's 60,000, where this would be 64,000. You make $4 more thousand a year on year 10 by getting a percent raise. And then let's say you put this out 20 years. Now all of a sudden you're $40. Here's where it starts to really make a difference. That $40 an hour is very different than 53. This would be equal to about $80,000 a year. This would be equal to about $106,000 a year. So that compounding is the difference between a linear and an exponential. It's the interest earning interest, or the raise earning a raise kind of a thing, year after year after year. So the more realistic version of this is this kind of a thing, where it's called a compound. You're compounding interest. It has this same feel. The difference is this was a raise one time a year. This is, let's say, more of a bank account or an investment or something. And you're earning interest maybe every month or every day or quarterly or something along those lines. Okay, so it's going to take your rate and it's going to break it up into these small little increments and pay you interest, okay, especially if it's an investment. But then this exponent is going to represent the total number of times you're going to get this interest added on. Okay, so for example, let me kind of go off to the side. So the A value is going to represent your accumulated amount, which is kind of the same thing as what this was. Your P always represents your initial amount, principal. So that P is principal in the financial world. It represents the same initial value as what we called it up here. This is like the most basic general version of it. This is very financially specific. And then there's that 1 plus a rate, but your rate is being broken up into how many times it's compounding per year. And then your exponent, your time, is if you had an investment for a year, but you were earning interest 12 times a year, then this power is going to be 12. If you were doing that for 5 years, then the power would be 60 because you'd get monthly increments for 5 years. Okay, so the types of things that they're going to talk about is an annual. If you are earning interest annually, then your N equals 1. If you're earning something semi-annual, then your N equals 2. If it's quarterly, then your N equals 4 times a year. It could be monthly, then your N equals 12, and it could be daily. Those are your most common kind of situations. Then your N is going to be 365 because you're going to break your interest rate into 365 equal little parts. All right. So what you have to do is just kind of pull that information out of a situation and then really just plug it into the equation. You just got to know what pieces are what. Okay. So it says we're going to use a compound interest formula, which is this, and a scientific method, to find the accumulated amount of an investment of $1,500. So that accumulated amount, or our initial investment, is $1,500. So that's our P. We're investing in an interest rate of 0.09. Okay, so I'm going to make that into a decimal version of it for 3 years. So our time equals 3. If the interest rate is compounded quarterly. Okay, now that 0.09 would just be if we got 9% at the end of the year and that was it. But our N is going to take this interest rate and break it into 4 equal parts. But we're also going to get more payments. Okay, so it's going to compound more. All right, it's going to compound a total of 12 times. So we're just going to plug all this into the formula. We got a 1,500, 1 plus our rate, which is 0.09. Our formula is automatically going to cut it into 4 equal little pieces. And then if you follow the steps on this, it's your N, which is 4 times per year, times your number of years. So 4 times 3. All right. So our final amount is us just plugging that into the calculator. So we're going to do 1,500 times 1 plus 0.09. Right, divided by 4. I don't have to worry about parentheses on this because the calculator is going to do order of operations perfectly, which means it's going to do division before it does addition. And then it's going to raise it to, and either I'm just going to put 12 there, or I'm going to do 4 times 3 and then get an answer. So that's going to compound that $1,500, and it's going to break it up into these quarterly little installments, adding on to the $1,500, and then earning interest over a period of 12 payments, 12 compounds, and then this is the amount we're going to get. Now we're going to treat it like money, so that 4 is not going to do anything to the 7. So we are looking at a final answer of 1,959.07 cents. All right. And that is how much this investment, if it was guaranteed to return 9% and compounded quarterly, that's exactly the amount that you would get. And real quick, what's the difference if you didn't get this quarterly? So if you didn't get this broken up, the difference would be you'd have 1,500, 1 plus 0.09. You wouldn't divide by anything. 1 plus 0.09. You wouldn't divide by anything because you're not breaking it up into little installments, and you wouldn't get 12 payments. You would only get 3 because it's 3 years. All right. So that would get you this. So the fact that we didn't compound it as often, we didn't get earning interest as many times as we did here, you don't ever make as much money. So the more times you can compound something, even if it's the exact same interest rate, the more times you can compound it, the better off you'll be. So probably the best situation would be if we could compound something daily. It would be pretty close to this, but it definitely would be higher than this. The biggest is if you can compound it any at all, then you're definitely going to get more money. Okay. So that's using the calculator and plugging it in. We have more examples, but that's kind of the basic idea of the difference between what a linear pattern is, which is an adding and subtracting pattern, versus an exponential, which is a multiplying kind of a pattern over and over and over again.